When we think about mining, our minds usually turn to vast open-pit mines on Earth or deep underground shafts where precious metals and minerals are extracted. But what if the next great mining frontier isn't on our planet at all? Imagine reaching beyond Earth's atmosphere to tap into resources stored in asteroids, rocky remnants from the early solar system. This idea, once the stuff of science fiction, is now being seriously studied by scientists, engineers, and space agencies. Understanding what asteroids contain and how we might access those materials is crucial to exploring whether space mining could become a reality. Asteroids are often described as planetary building blocks, leftovers from the time when planets like Earth were forming about 4.6 billion years ago. These small celestial bodies orbit the Sun, mostly within the asteroid belt located between Mars and Jupiter, although many others, called near-Earth asteroids, NEAs, have orbits closer to our planet. Their composition varies widely. Some resemble rocky bodies made mostly of silicate minerals, others are rich in metal, and some contain significant amounts of water trapped as ice or bound within minerals. One of the most compelling reasons to consider asteroid mining is the potential for resource extraction without the constraints of Earth's environmental and geographical limitations. On our planet, mining often involves significant ecological disruption, energy consumption, and logistical challenges related to transporting materials. In contrast, asteroids offer concentrations of materials that are not only diverse, but can be accessed in an environment where traditional mining problems might take on new dimensions, and also new solutions. Among the most valuable materials asteroids could provide are metals that are critical for modern technology. Platinum group metals, for instance, are rare and expensive on Earth, but are found in certain metallic asteroids in far greater quantities. These metals, including platinum, palladium, rhodium, and iridium, are essential for catalytic converters in cars, electronics manufacturing, and even medical equipment. The demand for these materials continues to grow as global industries expand, and recycling alone might not meet future requirements. But extracting metals from space rocks isn't as straightforward as digging with a pickaxe. Asteroids typically possess low gravity, meaning loose materials don't stay put in the same way they do on Earth. This unique factor requires innovative approaches to mining techniques and stabilization. Scientists are exploring robotic mining methods, where automated spacecraft could attach to an asteroid, break apart the surface, and collect material without risking human lives or heavy equipment. Water is another resource that makes asteroids particularly interesting targets, not just for commercial purposes, but for the future of space exploration itself. Many asteroids contain water in the form of ice or hydrated minerals, especially those that spent lengthy periods in colder regions of the solar system. Water is incredibly heavy and expensive to send from Earth into orbit, so acquiring it from space sources could dramatically reduce the costs involved in fuel and life support for spacecraft. In space, water has multiple uses. It can be split into hydrogen and oxygen via a process called electrolysis, then used as rocket propellant. This means asteroids could serve as gas stations in space, allowing spacecraft to refuel without making the long journey back to Earth. This would enable longer missions, such as manned missions to Mars or even crewed journeys to the outer solar system. In addition to metals and water, asteroids hold other materials of interest, like carbon compounds found in carbonaceous chondrite asteroids. These organic-rich bodies carry complex molecules that have intrigued scientists studying the origins of life. While mining for these materials is less likely to become immediately widespread, their scientific value contributes to the overall allure of asteroid exploration and utilization. The technological hurdles to mining asteroids remain significant. While robotic spacecraft have successfully landed on and sampled asteroids, such as Japan's Hayabusa missions and NASA's OSIRIS-RX mission, these projects primarily aim to study asteroid composition and return small samples to Earth. Scaling up from small sample retrieval to industrial mining involves challenges like capturing and processing large amounts of material and safely transporting it back to Earth or to orbital facilities. One avenue under study is in situ resource utilization, ISRU, a strategy that envisions using the materials mined directly on or near the asteroid to support further exploration. For example, metal extracted from an asteroid might be used to build structures or repair spacecraft in orbit, sidestepping the need to haul heavy building materials from Earth. NASA and private companies alike are investigating how ISRU could facilitate longer, more sustainable space missions. Economics is a key factor in whether asteroid mining will become viable. The cost of developing, launching, and operating mining missions is immense, and investors will expect a strong return on their investments. However, advances in rocketry, space robotics, and materials processing are steadily driving down costs. The availability of multiple asteroids of varying composition also means that the best targets can be selected for specific resources, optimizing mining efforts. Legal and ethical questions also arise when considering space mining. The Outer Space Treaty of 1967 establishes that celestial bodies are not subject to national appropriation, but recent interpretations and new laws in some countries, such as the U.S. Commercial Space Launch Competitiveness Act of 2015, provide companies with rights to resources extracted from space. The debate over how to regulate space mining and ensure it benefits all humanity is ongoing and will shape the pace and nature of this emerging industry. The potential benefits of asteroid mining extend beyond commercial interests. Space resources could support colonies on the Moon and Mars, reducing dependency on Earth supplies and making human presence beyond our planet more sustainable. They might even provide raw materials for manufacturing in space, where microgravity and vacuum conditions open possibilities for new materials and processes not feasible on Earth. In summary, the prospect of mining asteroids for metals and water carries both tremendous promise and significant challenges. Continuous advances in space technology, growing interest from private companies, and the strategic importance of off-world resources all suggest that asteroid mining could become a vital part of humanity's future in space. By studying and eventually utilizing these ancient solar system relics, we could open a new chapter not just in resource extraction, but in the ongoing human journey beyond Earth. As this field advances, the next steps will involve proving technologies at scale, creating sustainable business models, and crafting international rules to govern these activities peacefully and equitably. The transition from possibility to reality will require patience, innovation, and cooperation. But if successful, asteroid mining might one day become as common as mining on Earth is today. A critical aspect that often comes up when discussing asteroid mining is the question of how to actually get the extracted materials back to Earth, or alternatively, how to use them in space. Transport isn't just a logistical challenge, it's one that strongly affects the economics and feasibility of mining operations. Launching payloads from Earth remains expensive, despite substantial improvements in rocket technology, and shipping materials across millions of kilometers through space adds complexity. So, understanding the transport problem is essential to imagining how asteroid mining could work in practice. One approach is to mine asteroids that come relatively close to Earth's orbit, known as near-Earth asteroids or NEAs. These bodies are much easier to reach than main belt asteroids, which revolve between Mars and Jupiter, requiring less energy to travel there and back. Space agencies and private companies aiming to develop mining technology often prioritize accessibility, looking at asteroids whose orbits intersect or closely approach Earth. By selecting NEAs with the right properties, spacecraft could perform relatively short missions, reducing time and fuel costs. Once materials are extracted, bringing them back to Earth might involve packaging the resources into payloads small enough for re-entry or capture, or sending them to orbital facilities where they can be processed or stored. One concept involves placing a space habitat or orbital station in a stable region, such as a Lagrange point, where gravitational forces balance out to create a relatively stable location in space. There, mined materials could be refined and converted into usable products or fuels, supplying not just Earth, but also spacecraft traveling further into the solar system. Alternatively, some experts envision a future where the goal of asteroid mining isn't necessarily to return resources to Earth, but rather to use them in space to support human missions and infrastructure. For example, instead of bringing back tons of metal or water, extracted materials could be turned directly into rocket fuel, construction materials, or life support consumables for astronauts on space stations, lunar bases, or missions to Mars. This approach dramatically reduces the need to move heavy cargo over vast distances, which translates into significant savings in energy and cost. To understand why transporting resources back to Earth can be so challenging, it helps to grasp the concept of orbital mechanics. Spacecraft going to asteroids must fight not only Earth's gravity when leaving, but also align their trajectory to intercept the target asteroid's path around the Sun. Returning materials requires carefully timed transfer orbits so that the ship arrives back at Earth's vicinity at the right moment. The energy expenditure, measured in terms of delta V, a change in velocity, is a key consideration. Missions with lower delta V costs are more practical. Another element making asteroid mining difficult is the need to process materials in space under unfamiliar conditions. Unlike Earth's gravity and atmosphere, space is a microgravity, vacuum environment, which both complicates and offers opportunities. Mining in microgravity means that dust and small debris behave differently, floating away rather than settling on surfaces. Handling loose material requires careful engineering to prevent loss and contamination. On the other hand, zero gravity reduces the mechanical stress on mining hardware and enables techniques that wouldn't work on Earth, such as gentle scooping or vacuum-based collection systems. The processing itself, extracting metals from rock, separating water from minerals, refining elements, will require machines and processes adapted to operate remotely and autonomously, or with minimal human supervision. Already, some experimental concepts propose solar-powered extraction units that use concentrated sunlight to heat asteroid material and release volatiles like water vapor, which can then be captured and condensed. Others envision robotic smelters powered by electricity or microwaves to separate metals. These technologies are still developmental, but demonstrate that mining and refining in space might become possible without heavy, complex equipment. While early asteroid missions like Japan's Hayabusa and NASA's OSIRIS-Rx have provided critical knowledge about asteroid composition and surface conditions, they also highlighted the difficulty of working on such bodies. For instance, when OSIRIS-Rx touched down on the asteroid Bennu to collect samples, it had to overcome challenges like unexpected rock sizes and regolith properties. Scaling up from gathering tiny amounts for scientific study to industrial-scale mining operations will require significant advances in robotics, drilling, excavation, and material handling. The human factor also raises questions. Initially, asteroid mining will rely heavily on robotic and automated systems to avoid the enormous costs and risks of sending miners into deep space. However, as space infrastructure evolves and missions become longer and more complex, there might be scenarios in which astronauts assist with mining tasks, monitor equipment, or perform maintenance. Such human presence would increase the design requirements for habitats, life support, and safety features on or near mining sites. Besides the technical and operational hurdles, another vital ingredient for asteroid mining to flourish is the development of suitable market frameworks. For instance, metals extracted from asteroids have value only if they can be sold profitably, either on Earth or in space. The commodity markets will have to adapt to include space-sourced materials, and supply chains will need to evolve to manage delivery, distribution, and regulatory compliance. Interestingly, the influx of extraterrestrial metals could influence terrestrial markets. If asteroid mining delivers abundant supplies of rare metals like platinum, the global price could decrease, reshaping industries and potentially lessening pressures for environmentally damaging mining on Earth. However, this could be a double-edged sword, as companies invested in terrestrial mining might resist such changes. Coordinated policies and international agreements could be necessary to manage these transitions smoothly. Alongside metals, the harvesting of water and volatiles from asteroids could kickstart a robust space economy by enabling propellant depots in orbit. With refueling stations, spacecraft could reuse vehicles, cut costs, and extend mission durations. In fact, private ventures and some government initiatives are already exploring the feasibility of creating space gas stations, fueled by asteroid-extracted water. This would mark a profound shift from Earth-dependent space travel to more self-sufficient deep space exploration. This shift to utilizing space resources where they are found is often described as enabling a space economy that could sustain itself and grow beyond Earth support. Such an economy could facilitate activities like satellite construction, manufacturing of materials with unique microgravity properties, space tourism, and even scientific research. Mining asteroids could provide essential raw materials to feed these various sectors. However, before any asteroid mining operation can commence, understanding the detailed makeup of target asteroids is essential. These bodies vary not just in their mineral content, but in their structure. Whether they are solid rock, rubble piles held weakly together by gravity, or a mix of metals and ice. The integrity and characteristics of an asteroid directly affect how mining equipment can work on it. For example, drilling into a dense metallic asteroid differs greatly from excavating loose pebbles bound lightly by gravity. Missions aiming to scout and survey asteroids provide invaluable data, helping engineers develop specialized extraction methods. In addition to surveys, experiments simulating microgravity mining have taken place on Earth and aboard the International Space Station. These tests study how materials behave in low gravity and how to design tools that can dig, sift, separate, and store resources efficiently. The results inform future mission design, pointing toward the need for flexible and modular systems that can adapt to varying asteroid environments. Even with all these efforts, we must remember that the first asteroid mining ventures will be pioneering endeavors, likely in the form of demonstration missions. They will test hardware, analyze returns, and refine techniques. Early missions might only bring back small amounts of material, but will yield huge dividends in proving concepts and attracting investor confidence. Private companies like Planetary Resources and Deep Space Industries, now acquired or restructured, sparked a lot of excitement with ambitious plans to mine water and metals from NEAs. While neither company has yet initiated full-scale mining, their work spurred technological innovation, public interest, and laid groundwork for future players. Meanwhile, government programs and collaborations, notably NASA's ARM asteroid redirect mission, concepts, and ESA's proposed sample return missions, continue to push the boundaries of what is possible. An important reason behind this momentum is that space mining aligns well with broader goals of space exploration. For instance, establishing sustained human outposts on the Moon and Mars will require resources that are prohibitively expensive to launch exclusively from Earth. Asteroids could supply critical materials for building habitats, manufacturing spare parts, producing fuel, and growing food through systems supported by water resources. Beyond technical and economic aspects, asteroid mining invites us to reflect on Earth's place in a larger context. As humanity grows increasingly dependent on technology and raw materials, searching for these resources in space could ease the environmental strains back home. It's an opportunity to rethink how we manage finite resources, fostering sustainability on a cosmic scale. To sum up, the transportation and utilization of mined asteroid resources stand as both opportunities and hurdles in the path towards space mining. While bringing materials back to Earth faces challenges related to energy, distance, and cost. Using these resources in orbit or elsewhere in the solar system might prove more practical in the near term. Continued research, technological advancement, and thoughtful planning will determine whether asteroid mining can move from being a captivating possibility to a robust, everyday part of humanity's presence in space. Building on the complexities of transporting mined materials and the potential for in-space utilization, the question of how to extract resources efficiently from asteroids invites deeper examination. Unlike mining on Earth, which often relies on well-established machinery and techniques developed over centuries, asteroid mining must adapt to unique extraterrestrial conditions, shaping the very design of extraction systems. One significant challenge is the microgravity environment. Asteroids have gravitational pulls far weaker than Earth's, often just a fraction of 1%. This low gravity affects how mining equipment operates and how materials behave when disturbed. For example, drilling into or breaking the surface of an asteroid could send fragments and dust floating away into space, potentially losing valuable resources and creating hazards for equipment. The absence of strong gravity means that techniques common on Earth, such as using heavy machinery to crush or carry material, must be re-envisioned. To address this, engineers have proposed several innovative approaches tailored to asteroids' low-gravity settings. Instead of relying on direct mechanical excavation, some designs use methods like capturing loose regolith, the layer of loose dust and small rocks covering most asteroids, with specialized scoops or harpoons that can grab and contain material without relying on friction or weight. These tools need to be carefully designed to anchor onto the asteroid's surface during extraction, preventing the mining spacecraft from pushing off or drifting away due to reaction forces. Another promising idea involves heating and volatilizing materials to separate valuable compounds without heavy mechanical processing. By focusing sunlight with mirrors or utilizing powerful lasers, localized heating can vaporize water or other volatile substances trapped in minerals. The vapor can then be captured and condensed into liquid water for storage, fuel production, or other uses. This technique reduces the amount of equipment needed and sidesteps the problems of moving bulk materials in microgravity. Innovative concepts have also been developed for metallic asteroids, which might contain significant quantities of nickel, iron, and platinum group metals embedded within a dense matrix. For these, approaches such as magnetic separation could be feasible. Since many metals are ferromagnetic, magnets could be used to pull and sort metallic particles after breaking up the surface material. Additionally, electrostatic methods might help separate and collect fine particles based on their charge differences. These technological strategies do not exist in a vacuum. In fact, decades of terrestrial mining provide valuable lessons, especially from extreme environments like the deep ocean or polar regions, where traditional methods struggle and specialized robotics must operate autonomously. The robotics used in planetary exploration, such as Mars rovers, are another source of inspiration. Combining autonomous navigation, remote operation, and adaptive tools tailored to changing surface conditions is vital when human intervention is limited due to distance and communications lag. To further complicate extraction, asteroid surfaces are often covered in loose, uneven regolith composed of particles ranging from fine dust to large boulders. This material isn't tightly bound by gravity, and the mechanical strength of the asteroid's surface can vary widely. Some asteroids, known as rubble piles, are actually loose agglomerations of rock fragments held together weakly by gravity and possibly subtle cohesive forces. Mining such a structure would require delicate interaction to avoid destabilizing the entire body or causing material loss. On the other hand, some asteroids exhibit hard, compact surfaces that might demand drilling or cutting technologies resembling terrestrial mining, but adapted for vacuum and low gravity. The operation of mining equipment in space entails coping with the vacuum environment's effects on materials and machinery. For example, lubricants commonly used in Earth-based machinery can evaporate or degrade quickly in space, so engineers must use special lubricants suited for vacuum or implement dry, solid lubricant bearings. Electronics and sensors employed in mining tools must be radiation-hardened to withstand the space environment, while maintaining reliable operation over extended periods. Power generation is another design consideration. Mining processes often require substantial energy, and on asteroids, solar energy is generally the most accessible power source. Solar panels can be deployed on or near the mining site, but their output varies with the asteroid's distance from the Sun and can be limited during periods of shadow or rotation. Energy storage systems, such as batteries, might be needed to maintain continuous operation, as well as mechanisms to track and optimize solar panel orientation. Looking ahead, the integration of these technologies suggests a phased approach to asteroid mining that begins with small-scale, low-risk operations. Demonstration missions focused on extracting limited quantities of water or metals would validate methods and provide crucial data for refining mining systems. Success in these early activities is expected to build confidence for larger, industrial-scale operations. Supporting these ambitions, some space agencies and private companies are actively developing testbed technologies. For example, NASA's Space Technology Mission Directorate has funded research into autonomous robotics, resource extraction prototypes, and surface characterization tools. Meanwhile, European initiatives like the European Space Agency's Prospect package for resource observation, in situ analysis and prospecting for exploration, commercial exploitation and transportation instrument series aim to characterize water and volatile distribution on lunar and asteroid surfaces, directly aiding resource extraction planning. An inspiring demonstration of the technological progress is the success of recent sample return missions that involved brief physical contact with asteroid surfaces. Japan's Hayabusa mission collected samples by firing a projectile into asteroid Ryugu to blast material into a collection chamber, while NASA's OSIRIS-RX mission used a robotic arm mechanism called the Touch-and-Go Sample Acquisition Mechanism, TAGSAM, to lift surface material from the asteroid Bennu. These missions underscored the feasibility of interacting with asteroid surfaces and retrieving material, though on a much smaller scale than mining operations would require. To transition from demonstration to practical mining, autonomous spacecraft will need to conduct sustained operations over weeks or months, progressively extracting larger quantities of material. Continuous operation in such harsh, remote environments requires systems capable of self-diagnosis, repair, and adaptive responses to unexpected surface conditions, a significant leap in robotics and artificial intelligence. Collaboration between private industry, academia, and governmental space agencies appears crucial for overcoming these technical and operational challenges. The cost of developing, launching, and operating mining spacecraft is substantial, making partnerships vital for sharing expertise and financial risk. Moreover, information sharing and standardization around mining techniques and equipment could accelerate the maturation of the sector. Concurrently, political and legal frameworks will need to support these technologies by defining property rights, resource ownership, and dispute resolution mechanisms. Without clear regulations, investments in mining technology may face uncertainties hindering development. International bodies like the United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, are engaged in discussions, striving to balance encouraging innovation while maintaining shared access to space resources. The extraction methods and equipment also connect directly to the attractiveness of different asteroid targets. Detailed surveys and sample analyses allow mission planners to prioritize asteroids based on resource content, physical characteristics, and orbital accessibility. For example, an asteroid with abundant water ice near Earth and a stable surface might be chosen first to demonstrate water extraction and processing. In contrast, a metal-rich asteroid with a high but accessible orbit could be targeted later for metal recovery operations. Advances in telescopes, radar observations, and spacecraft reconnaissance enrich the catalog of known asteroids and refine estimates of their compositions. These observational efforts are dynamic. As new candidate asteroids are discovered and characterized, the pool of potential mining targets evolves. By integrating scientific knowledge from astronomy, geology, and mining engineering, mission designs become increasingly tailored and optimized. In summary, asteroid resource extraction is far from a simple extension of terrestrial mining. It demands innovative technologies and methods uniquely suited to operate in microgravity, vacuum, and radiation-heavy space environments. From gentle scooping and heating volatiles to sophisticated autonomous robotics working on the challenging, varied surfaces of asteroids, the technological landscape is rich and evolving. These innovative extraction techniques, combined with advances in reconnaissance and material characterization, are critical stepping stones toward making asteroid mining a practical venture. While the technical methods of extraction and processing are fundamental, equally important is the question of what to do with the materials once they have been mined. The logistics of handling, storing, and transporting these resources pose considerable challenges and influence every aspect of the mining mission's design and objectives. One important concept in this regard is the idea of in-space manufacturing, which envisions turning raw asteroid materials directly into useful products near the source, rather than shipping raw ore back to Earth. This could involve using extracted metals to 3D print components for spacecraft, satellites, or even habitat modules in orbit. By manufacturing in space, the costly step of launching heavy materials out of Earth's gravity well, or sending raw material over large distances, is substantially reduced. NASA and other research institutions are actively experimenting with 3D printing technologies that could operate in microgravity and vacuum conditions. For instance, using metal powders or regolith simulants, advanced printers could produce structural parts layer by layer. This approach holds exciting potential for scaling construction efforts in orbit or on planetary surfaces like the Moon and Mars, which might rely on asteroid-sourced feedstock. Moreover, water extracted from asteroids does not need to be brought home either. Instead, it could be stored at orbital fuel depots and used for green rocket fuel production via electrolysis, splitting water into hydrogen and oxygen. These propellants can then refuel spacecraft, enabling longer missions or launching payloads deeper into the solar system with reduced reliance on Earth supplies. Fuel depots in orbit stand to revolutionize space logistics. Currently, spacecraft expend the majority of their fuel simply escaping Earth's gravity. If water refueling stations were positioned strategically, such as at the Earth-Moon Lagrange points or in low Earth orbit, space missions could operate in a more shuttle-like manner. Mining asteroids to supply these depots would create a sustainable cycle for spacecraft refueling and maintenance. An illustrative example of this concept is the long-time vision of citizens of space, supported by orbital infrastructure. A spacecraft could launch from Earth with minimal fuel, dock at an orbital fuel station replenished by asteroid-mined water, then proceed toward destinations such as asteroids, the Moon, or Mars. After completing its mission, it could return to the station rather than Earth, refuel, and embark again. Such operational flexibility is a crucial step for building an enduring space economy. Still, bringing resources back to Earth's surface remains a compelling goal, especially for rare metals and minerals that have high terrestrial value. Successfully returning materials requires careful planning around re-entry to avoid destruction or loss. Spacecraft carrying mined payloads must be designed to safely decelerate from orbital speeds and survive atmospheric entry without contamination or damage. One approach under study is to package harvested materials into small capsules, similar to how sample return missions operate but on a larger scale. These capsules would detach from a mothership orbiting Earth and descend with heat shields and parachutes. Once on Earth, the collected materials could enter existing supply chains for use in manufacturing electronics, automotive catalytic converters, or even new fields like advanced computing. Alternatively, some mission concepts propose combining mined materials with other manufacturing processes in orbit, forming pre-assembled components or even larger structures before delivery to Earth's surface. This value-added approach improves payload mass efficiency and reduces handling complexity. However, it also pushes the technological envelope for robotic assembly in space and requires highly precise control systems. The question of where to process mined materials, on the asteroid, in orbit, or on Earth, depends on factors such as the type of resource, mission duration, and economic feasibility. Processing on the asteroid itself, known as in situ processing, minimizes transportation, but demands complex, autonomous factories capable of operating independently in a harsh environment. Orbital processing offers a middle ground, where stable platforms and power sources support more sophisticated refining equipment. Such orbital processing facilities could function akin to space-based refineries or fabrication plants, using solar power, advanced robotics, and automation. These platforms would refine raw materials, generate propellants, and assemble components, acting as hubs in an expanding network of space infrastructure. The energy and resource flows in this system would rely heavily on asteroid mining, creating interdependent relationships between mining missions, manufacturing outposts, and exploration vessels. Economic models for this space-based supply chain are still in development, but often involve partnerships across private companies, governments, and research organizations. Funding schemes may include government contracts for services like propellant supply, commercial agreements for precious metals, or even emerging markets related to satellite repair and upgrade using asteroid-derived components. Despite the promising potential, managing the stability and security of this supply chain brings its own challenges. Space debris, harsh environmental conditions, and potential competitor activity all must be accounted for within operational plans. Robust communication systems and redundancy will be necessary to maintain continuous mining and processing operations over extended periods. Looking further ahead, the notion of self-sufficiency in space hinges greatly on the ability to recycle and repurpose mined materials effectively. As human presence beyond Earth grows, whether through orbital habitats, lunar bases, or Martian colonies, the demand for building materials, water, and fuel will skyrocket. Mining asteroids could meet these needs by creating a cyclical, sustainable resource economy, reducing the amount required to be launched from Earth and ensuring ongoing viability. Additionally, the environmental benefits of off-world mining could be substantial. By relieving some resource extraction pressure on Earth, asteroid mining might reduce ecological damage like habitat destruction, pollution, and resource depletion. However, this vision requires careful oversight to ensure that space activities themselves do not lead to new forms of contamination or degradation. One area of active research involves understanding how dust and debris created by mining operations in microgravity behave and how to contain them. Left uncontrolled, these particles could pose collision risks to operational equipment or contaminate scientific instruments. Developing dust mitigation technologies and containment strategies is therefore a vital element in ensuring safe and sustainable asteroid mining practices. International collaboration and shared standards for mining operations, waste management, and resource utilization will help preserve space as a safe and usable environment for all. Coordination among spacefaring nations and commercial entities is essential because the orbital pathways, planetary surfaces, and deep space zones used for mining and processing are interconnected environments affected by everyone's activities. In sum, extracting resources from asteroids is only the start. The full promise of asteroid mining lies in integrating extraction, processing, storage, transport, and utilization into a coherent system, an emerging space infrastructure that supports scientific, commercial, and exploratory objectives. This system could transform how humanity accesses raw materials, enables sustainable space exploration, and opens new economic frontiers beyond our planet. The next question's future missions will address include optimizing supply chains, increasing autonomy of mining and manufacturing systems, minimizing costs, and ensuring the environmental stewardship of space resources. Technological innovation, investment, and international cooperation all play pivotal roles as we move closer toward turning asteroid mining from concept into reality. To advance asteroid mining beyond theoretical frameworks and small-scale demonstration missions, a crucial component is the development and deployment of autonomous robotics capable of carrying out complex mining operations without direct human intervention. The vast distances involved, combined with communication delays that can range from several minutes up to over an hour for distant targets, mean that real-time control from Earth is impractical. Therefore, mining spacecraft must be equipped with sophisticated onboard systems that enable them to navigate, excavate, process, and manage resources independently. These robotic systems require a blend of precision, adaptability, and resilience. Precision is necessary to target specific areas rich in desirable materials, minimizing wasted effort and material loss. Adaptability ensures that robotic miners can respond to unexpected surface conditions, such as sudden changes in regolith texture, unanticipated rock formations, or irregular gravitational fields. Resilience is vital for long-duration missions where maintenance and repair opportunities are limited or non-existent. One approach to achieving this level of autonomy is through a combination of artificial intelligence, AI, machine learning algorithms, and advanced sensor arrays. Sensors can detect surface composition, topography, and mechanical properties, feeding this data into AI systems that plan and adjust mining activities in real time. For example, an autonomous rover might shift from excavation to sample collection if it detects an increase in valuable metal concentration, or switch to a safer operational mode if hazardous instability in the asteroid's structure is sensed. NASA and private companies alike have been making strides in autonomous robotics tailored to space operations. Projects such as NASA's RASSOR, Regolith Advanced Surface Systems Operations Robot, investigate robotic digging and regolith handling in microgravity, incorporating fail-safe mechanisms and adaptable control schemes. These prototypes simulate lunar and asteroid conditions, yielding insights into energy efficiency and operational reliability. Swarm robotics is another promising paradigm. Instead of a single large mining machine, clusters of smaller, cooperative robots could work together to perform excavation, transport, and processing tasks. Swarms would spread operational risks. If one unit fails, others can continue working and increase efficiency by dividing labor. Their distributed nature also allows flexibility, wherein the swarm can reorganize to tackle different tasks or avoid obstacles. In addition to robotic mining, transportation within the mining site is essential. Material handling systems must account for low gravity by using specialized anchoring, electromagnetic conveyors, or containment chambers to move loosened material without loss. For finer particles, electrostatic forces can be used to manipulate regolith dust, enabling collection and transfer without physical contact that might send particles drifting into space. Power considerations also influence robotics design. Given the limited energy availability in deep space, many mining systems rely on deploying large solar arrays or nuclear power units. Nuclear options can provide consistent output regardless of solar intensity or shadowing, making them attractive for operations beyond the asteroid belt or during long asteroid night periods. However, they introduce complexities related to safety, launch approval, and cost. An illustrative potential mission sequence might involve a mother ship acting as a mobile command and processing station, deploying robotic miners that anchor onto an asteroid's surface. These robots would break apart material, deliver it to processing units that extract water or metals, and transfer refined products back to storage. The mothership could then deliver those products to fuel depots in orbit or prepare them for Earth return. Long-duration autonomy not only depends on onboard computing, but also on fault diagnosis and self-repair abilities. Robotic miners must detect mechanical wear, perform diagnostics, and execute repairs with limited spare parts or self-fabricated replacements. This capability requires modular designs, redundancy, and innovations in robotic dexterity. Research into 3D printing and additive manufacturing in microgravity contributes to the vision of machines fabricating parts of themselves, reducing dependence on resupply missions. Environmentally, minimizing the production of orbital debris or surface contamination is imperative. Uncontrolled debris created by mining operations could jeopardize satellites, other space missions, or even future mining activities. Thus, robotics must incorporate dust suppression systems, containment strategies, and fail-safe shutdown protocols if unexpected events occur. Apart from technology, mission planning must integrate the orbital and rotational dynamics of the targeted asteroid for optimal robotic operation. Some asteroids rotate rapidly, and this rotation affects the stability of mining equipment and the movement of processed materials. In some cases, the mission design might involve temporarily altering an asteroid's spin or trajectory to create safer and more efficient mining conditions, though such maneuvers are complex and resource-intensive. Aside from robots, local human presence remains a longer-term consideration. Although current efforts emphasize remote and autonomous missions, astronauts could one day supplement robotic mining by performing complex repairs, supervising operations, and addressing unexpected challenges. Human involvement would require habitat modules equipped with radiation shielding, life support, and communication systems capable of functioning independently for extended periods. Integrating humans and robots in asteroid mining raises further design challenges, including safety against microgravity hazards, exposure to cosmic radiation, and psychological impacts of isolation. Training astronauts for these environments involves new protocols and specialized skills distinct from terrestrial mining or even lunar or Martian surface operations. In parallel with technological development, scientific exploration plays a key role in refining asteroid mining prospects. Missions that survey asteroids in detail provide vital data about mineralogy, surface cohesion, porosity, and internal structure. Such information instructs robotics design, resource estimation, and mining strategy. For example, radar tomography can reveal whether an asteroid is monolithic or a loosely bound rubble pile, influencing the approach to excavation. In this way, asteroid mining sits at the intersection of multiple scientific disciplines. Planetary geology guides understanding mineral distributions. Materials science informs extraction and processing techniques. Robotics and computer science develop the autonomous systems, and aerospace engineering designs deployment and transport. Collaborations between these fields, supported by institutions like NASA, ESA, and private industry, foster innovative solutions. For instance, international partnerships might pool funding and expertise to launch a series of demonstration mining missions, progressively advancing capability while sharing risks. As with any frontier, unexpected discoveries will shape progress. New asteroid types, novel resource deposits, or unpredicted surface phenomena could present opportunities or obstacles. Accordingly, flexibility and continuous learning will be essential themes as asteroid mining evolves from an aspiration to an operational reality. Altogether, the shift towards autonomous, adaptable robotics represents the technological backbone for unlocking asteroid resources. These systems must reliably perform in environments hostile to humans, with challenges ranging from microgravity and vacuum to radiation and dust. By innovating in autonomy, material handling, power management, and fault tolerance, we move closer to establishing functional mining outposts beyond Earth, laying the foundation for a sustainable presence in space. As we refine the technological capabilities for asteroid mining, another pivotal consideration emerges: sustainability and environmental stewardship beyond Earth. While the space environment may seem vast and empty, it is not immune to the consequences of human activity. The introduction of large-scale industrial operations in space, such as mining, necessitates an awareness of potential environmental impacts and the development of best practices to mitigate them. One key aspect concerns the generation and management of debris, both on asteroids and in orbit. Mining operations inherently disturb surfaces, releasing dust, rock fragments, and possibly volatile molecules. In microgravity, these particles can drift uncontrollably, posing hazards to equipment and spacecraft. Even tiny grains of dust moving at high speeds can damage sensitive instruments or solar panels, rendering costly machines unusable. Therefore, mining missions must include systems for dust capture, containment, and controlled disposal. Strategies might involve enclosing mining areas within containment structures, or using electrostatic or magnetic fields to corral fine particles. Drawing lessons from the International Space Station, where micrometeoroids and orbital debris are constant threats, engineers are developing shielding and cleaning methodologies that could adapt to mining contexts. The absence of an atmosphere complicates these efforts, since there is no natural drag to slow escaping debris, making containment all the more critical. Moreover, the cumulative effect of repeated mining missions poses questions about the long-term alteration of asteroid orbits and spin rates. Since asteroids are small and loosely bound, removing mass from specific regions could subtly change their trajectories or rotational dynamics. Any orbit perturbation must be carefully monitored to prevent accidental collisions with other space objects or Earth. Agencies responsible for planetary defense already track near-Earth objects closely. Integrating mining-induced changes into their models will be necessary. Beyond debris and orbital dynamics, the preservation of scientific value also warrants attention. Asteroids serve as time capsules offering clues about the early solar system, and some may harbor organic compounds related to the origins of life. Extensive mining could destroy or permanently alter such information sources. To balance resource utilization with scientific inquiry, policies could designate certain asteroids, or regions within them, as protected, enabling research to continue unimpeded. This leads to broader emerging discussions about space environmental ethics. Just as we have gradually developed awareness and regulations regarding sustainable activities on Earth, there is growing recognition that human expansion into space should avoid reckless exploitation. International working groups, academic researchers, and space policy organizations are beginning to draft frameworks to ensure responsible stewardship of extraterrestrial environments. Such frameworks might include guidelines on the types of allowed extraction, limits on resource removal rates, reclamation or surface rehabilitation expectations, and monitoring requirements. The concept of off-world environmental impact assessments could become standard practice before approving mining missions. This proactive approach acknowledges that while space is not an infinite resource dump, it is a shared domain requiring ethical consideration. On an economic level, environmental stewardship intersects with the long-term viability of asteroid mining businesses. Actions that lead to contamination, site exhaustion, or satellite damages could provoke liabilities, loss of reputation, or international conflicts, all detrimental to the nascent space mining industry. Proactively adopting sustainable practices can build trust among investors, governments, and the public. International cooperation will be crucial to enforce and standardize these environmental safeguards. Because space activities transcend national borders, unilateral actions are insufficient to manage common resources effectively. The ongoing dialogues within the United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, as well as initiatives like the Artemis Accords, which establish norms for lunar exploration, signal the beginnings of multilateral governance efforts that may extend to asteroid mining. These diplomatic efforts aim to balance the encouragement of innovation and commercial development with preserving the peaceful, scientific, and sustainable use of space. Encouraging transparency, shared data, and communication between mining operators will help prevent conflicts and duplicative or detrimental exploitation. In parallel, emerging legal frameworks may define liability rules, licensing requirements, and dispute resolution mechanisms linked to environmental impacts. Looking back at Earth's own history provides instructive analogies. The Industrial Revolution and subsequent decades witnessed rapid resource extraction, accelerating economic growth, but causing environmental degradation. Efforts to develop environmental regulations, pollution controls, and conservation movements arose as society recognized these consequences. Space mining invites an opportunity to apply these lessons proactively, avoiding similar pitfalls on new frontiers. Of course, developing and implementing robust environmental safeguards in space mining require technology tailored to monitoring and control in remote, harsh space environments. Advanced sensors capable of detecting dust emissions, radiation leaks, or changes in asteroid mass distribution will be necessary. Distributed monitoring systems on mining spacecraft, orbital platforms, or even within constellation networks could provide real-time data to mission control and regulatory bodies. Artificial intelligence and machine learning could support assessment and compliance verification, automating detection of deviations from planned activities or unexpected environmental disturbances. This would facilitate early intervention and continuous adaptive management, enhancing safety and environmental protection while maintaining operational efficiencies. Beyond the technical and policy aspects, cultivating a spacefaring culture that values sustainability and responsibility is equally important. Encouraging education, awareness, and ethical discourse among scientists, engineers, entrepreneurs, and policymakers will foster a mindset that integrates environmental considerations naturally into design and mission decisions. Turning from environmental concerns, the topic of workforce and economic supply chains for asteroid mining deserves attention as the industry develops. Building and operating mining missions requires a diverse array of skilled professionals, ranging from aerospace engineers and planetary scientists to roboticists, data analysts, and legal experts. Training and sustaining such a workforce demands investment in education and capacity-building programs focused on space resource utilization. Further, asteroid mining will extend supply chain networks beyond Earth's traditional structures. Materials processing, component manufacturing, spacecraft construction, and launch services may become more distributed globally and eventually include in-space manufacturing and assembly. This shift challenges current business models and demands innovative contracting, procurement, and quality control processes that integrate terrestrial and extraterrestrial operations. The potential economic ripple effects also invite consideration. For example, introducing asteroid-derived metals into global markets might disrupt traditional mining sectors, shift employment patterns, or stimulate new industries related to space infrastructure, propellant production, and advanced manufacturing. Policymakers and economists will need to analyze these dynamics to mitigate negative impacts and capitalize on growth opportunities. Moreover, financing asteroid mining ventures presents notable challenges. The capital required for research, development, launch, and operation is substantial, and returns hinge on demonstrating reliable supply and market demand. Early-stage mining companies must navigate high risks, uncertain regulatory environments, and technological uncertainties. Access to venture capital, government grants, and public-private partnerships will be instrumental. Insurance markets will also evolve to cover novel space risks, including hardware failure, launch accidents, or payload loss. Standardizing risk assessment and mitigation strategies will support investment confidence and operational resilience. The development of reusable launch systems, reduced costs in spacecraft construction, and advances in propulsion all contribute to lowering these barriers over time. Alongside economic frameworks, public engagement and education play a key role in building support for asteroid mining. Awareness campaigns highlighting the scientific benefits, economic potential, and environmental considerations help demystify space mining and address concerns about space exploitation. Thoughtful communication can inspire a new generation to pursue space-related careers, increasing the talent pool and societal investment in space exploration. Finally, asteroid mining is poised to act as a catalyst for broader space settlement and exploration ambitions. Access to local resources reduces dependence on Earth's substantial launch costs and supplies, enabling missions of greater scale and duration. This resource independence could accelerate the establishment of lunar bases, Mars colonies, or even deep space habitats. The availability of water and metals from asteroids supports habitation, life support, manufacturing, and energy generation, key foundations for sustaining life far from Earth. As technologies mature, infrastructure grows, and regulatory frameworks solidify, asteroid mining could transition from pioneering experiments to commercial realities, fueling an expanding space economy. This development promises profound transformations not just in where we source raw materials, but in how humanity lives, works, and thrives beyond our home planet. The journey toward that future is complex and multifaceted, involving engineering breakthroughs, legal evolution, economic ingenuity, environmental responsibility, and cultural growth. Each step forward unfolds new challenges and insights, inviting creative problem-solving underpinned by scientific rigor and cooperation. In this way, mining asteroids is not merely about extracting valuable resources. It is about advancing humanity's capability to sustainably operate beyond Earth, opening new chapters in exploration, commerce, and discovery. The coming decades will reveal how this vision evolves, shaped by technologies developed and choices made by researchers, entrepreneurs, policymakers, and global communities working together. As the concept of asteroid mining becomes more tangible, attention is increasingly turning toward the economic viability and market dynamics that will underpin this emerging industry. While the technical hurdles are immense, they must be evaluated alongside the financial realities of launching, mining, processing, and transporting extraterrestrial resources. Understanding these economic factors helps clarify when and how asteroid mining could transition from experimental missions to sustainable commercial enterprises. One of the fundamental economic questions involves cost versus value. How much will it cost to extract resources from an asteroid and transport them either back to Earth or to orbital facilities? And will the sale or utilization of those resources generate sufficient revenue to justify those expenses? Launching payloads from Earth currently represents the largest share of space mission costs, often ranging from tens to hundreds of millions of dollars, depending on mass and destination. While recycling and resource efficiency reduce some burdens, the upfront investment for spacecraft, mining equipment, and processing infrastructure remains high. Advances in reusable launch vehicles, exemplified by companies like SpaceX with their Falcon 9 and Falcon Heavy rockets, are driving costs down, making initial missions more affordable. The planned development of next-generation heavy-lift rockets from both private firms and government agencies will further improve access to space. Still, until economies of scale emerge and operational experience accumulates, asteroid mining remains a high-risk, high-reward proposition. Market demand also plays a critical role. For metals like platinum, palladium, and rare earth elements, high prices and growing industrial demand could motivate investment in asteroid sources, particularly if terrestrial reserves become scarcer or more expensive to extract. However, introducing large quantities of these metals into Earth's market could disrupt prices and economic models. As sudden supply influxes might depress value, affecting profitability. This paradox underscores the need for carefully phased mining activities and robust market analysis. In contrast, resources like water and volatiles mined for in-space use present a somewhat different economic profile. Their value arises primarily in the context of supporting further space exploration and infrastructure, rather than direct sales on Earth. For example, propellant produced from asteroid water at orbital depots could reduce mission costs dramatically, creating a market of spacecraft operators willing to pay for reliable, locally sourced fuel. Here, the customer base is less global commodity markets and more niche space logistics providers. Another intriguing economic feature is the potential for asteroid mining to stimulate entirely new markets not yet developed. For instance, 3D printing of advanced materials in orbit using asteroid-derived metals could enable manufacturing specialty parts uniquely suited to space conditions. Such capabilities might support satellite repair, construction of large space structures, or even luxury goods for space tourism, expanding the market landscape beyond traditional mining commodities. Despite these promising opportunities, the early stage of the industry presents challenges attracting sufficient capital investment. Venture capitalists and other financial backers weigh risks, development timelines, and regulatory uncertainties. Some argue that initial government support or subsidies may be essential to catalyze the sector, providing de-risking mechanisms that encourage private participation. Governments have begun to acknowledge this role, investing in research and demonstration projects, offering contracts and facilitating technology transfer. For example, NASA's interest in advancing in situ resource utilization, ISRU, aligns with goals to reduce mission costs and enable extended presence on the Moon and Mars. Public-private partnerships may prove instrumental in bridging the gap between pioneering demonstration missions and routine commercial mining operations. Another factor influencing economic viability is mission cadence, the frequency and duration of mining missions. Sustainable operations require regular launches and returns, ensuring consistent supply and revenue flows. Missions with long turnaround times or sporadic outputs reduce financial predictability and increase operational risks. Therefore, developing rapid turnaround vehicles, efficient processing technologies, and reusable components are all necessary to move toward industrial-scale mining. Insurance and risk management also feature prominently in economic planning. Space missions face numerous uncertainties: launch failures, equipment malfunctions, off-nominal asteroid behaviors, or data inaccuracies leading to unexpected surface conditions. To attract investment and enable lending, insurance products tailored to space mining risks will need to evolve, balancing coverage with manageable premiums. Such developments are currently in their infancy, reflecting the novelty of the sector. Meanwhile, the legal and regulatory landscape adds layers of uncertainty that impact business models. The evolving patchwork of international treaties, national laws, and private claims to space resources creates a complex environment where legal disputes could arise. Companies must navigate issues such as licensing, property rights, liability for environmental impacts, and potential conflicts over overlapping claims. Clarity and stability in these domains will enhance economic confidence and investment security. Beyond terrestrial markets, in space commerce increasingly factors into economic calculations. The concept of space as a market involves transactions among various space actors, satellite operators, exploration agencies, manufacturing firms, and fuel providers, who might become customers for mined resources. This evolving ecosystem could provide diversified revenue streams and enable economies of scale, offsetting some risks linked to earthbound commodity markets. The global nature of space mining also raises strategic considerations. Countries with strong aerospace industries and access to spaceports may hold advantages in developing infrastructure and operations, potentially influencing geopolitical dynamics. Space resources could become elements of national pride or strategic asset portfolios, similar to terrestrial natural resources, adding motivation for governments to support their domestic industries through funding and regulatory support. At the same time, competition among private companies, both established aerospace entities and new space startups, spurs innovation and cost reduction. This competitive environment fosters rapid technology development but also increases market uncertainty. Companies must balance secrecy for competitive advantage with collaboration to accelerate sector-wide progress, a tension common in emerging industries. To illustrate economic complexities, consider a hypothetical mining mission targeting a near-Earth asteroid rich in water. The spacecraft must first be launched and propelled, requiring fuel and infrastructure, then must rendezvous with the asteroid and extract water using autonomous systems. After processing, the water might be transported to an orbital fuel depot and sold to space missions needing in-space refueling. The total mission cost could reach hundreds of millions of dollars, but with repeated missions over time and multiple clients purchasing propellant, the operation could become profitable. A single successful mission might not recoup investment, but a sustained program could transform the economics. Alternatively, mining platinum group metals and returning them safely to Earth involves additional complexities. The cost and risk of safe re-entry capsules, market price fluctuation, and competition with terrestrial mining all influence potential profitability. Additionally, refining and incorporating returned metals into global supply chains represent logistical challenges. Only if the supply is reliably maintained at scale and costs are contained will such ventures become viable. These realities point toward a gradual development path, where initial mining activities focus on demonstrable in-space uses like propellant production and construction materials, laying the groundwork for larger-scale extraction and Earth return operations. Phased approaches reduce financial exposure and provide valuable data to refine economic models and technological designs. In summary, the economic dimension of asteroid mining is a complex interplay of costs, market demand, technology readiness, regulatory frameworks, and geopolitical factors. While promising, it requires coordinated effort from industry stakeholders, governments, investors, and researchers to develop sustainable business models. With advancing technology, falling launch costs, and growing space infrastructure, asteroid mining may emerge as a significant element of the future space and terrestrial economies, turning a once speculative idea into a commercial reality. Yet, alongside economics, another future-facing consideration involves the integration of asteroid mining within broader space exploration ambitions, specifically how space resources could enable human presence beyond Earth on a lasting scale. Understanding this relationship sheds light on the strategic importance of asteroid mining beyond immediate commercial returns. Sustaining humans in space for months or years requires substantial supplies of water, breathable air, food, building materials, and energy. Shipping these necessities from Earth is prohibitively costly and limits mission duration and scale. Asteroids, as abundant repositories of volatiles and materials, offer a potential solution to this supply bottleneck. For example, the water extracted from asteroids can support life support systems by providing drinking water, oxygen through electrolysis, and hygiene supplies. Constructing habitats on the Moon or Mars may depend on metals and regolith-derived materials sourced from asteroids to reduce reliance on expensive Earth launches. The ability to live off the land, in this case off the asteroid, represents a paradigm shift in mission planning and sustainability. Plans for lunar bases under initiatives like NASA's Artemis program envision leveraging lunar resources, but asteroid mining could complement or supplement these efforts by providing materials not readily accessible on the Moon. Moreover, deep space habitats or Mars transit vehicles outfitted with asteroid-derived supplies could extend mission durations, reduce payload mass, and improve safety margins. In addition, asteroid mining plays a potential role in planetary defense. Techniques being developed to interact with asteroid surfaces, landing, drilling, or altering trajectories, enhance our ability to mitigate threats from potentially hazardous asteroids. The overlap between defense capabilities and resource extraction may lead to dual-use technologies and shared mission architectures. The deep connection between asteroid mining and human exploration underscores its strategic priority for many space agencies. Governments increasingly view space resources not only as commercial commodities, but as critical infrastructure for expanding human civilization beyond Earth. This perspective drives funding, international collaboration, and policy development aimed at integrating asteroid mining within the broader space ecosystem. In conclusion, asteroid mining sits at the nexus of technology, economics, exploration, and sustainability. Its successful realization requires converging advances in autonomous robotics, resource processing, market development, and legal frameworks, supported by a vision of humanity's expanding frontier. While challenges remain substantial, progress over recent decades offers optimism that asteroid mining will shift from theoretical discussion to active practice, fundamentally altering how we acquire and use resources both on Earth and in space. Looking beyond the immediate horizon, one of the most intriguing and practical prospects for asteroid mining lies in its potential to support the construction and operation of infrastructure in space itself. As humanity contemplates the establishment of permanent outposts on the Moon, Mars, and even free-floating habitats in orbit, the necessity for building materials and propellants in space becomes ever more apparent. Asteroid mining could play a crucial role in making these ambitions financially and technically feasible. But what exactly would constructing in space entail, and how could materials from asteroids facilitate this process? The concept involves utilizing resources harvested from asteroids, metals, silicates, and volatiles, to fabricate components for spacecraft, habitats, and tools directly in orbit or on planetary surfaces. This approach, often termed space manufacturing or in situ fabrication, significantly reduces the need to launch heavy materials from Earth, which is the costliest part of any space mission due to Earth's strong gravity. Metals like iron, nickel, and cobalt, commonly found in metallic asteroids, could be refined and processed into structural elements needed for building frameworks, radiation shielding, or machinery parts. Silicate-rich asteroids could provide raw materials for manufacturing glass, ceramics, or concrete-like substances, using techniques adapted for microgravity and vacuum environments. This diversity of materials forms the basis for versatile construction capabilities beyond Earth. The practical advantages here are compelling. Launching a ton of material into space costs thousands of dollars even with modern reusable rockets. Using asteroid-derived materials converts a prohibitively expensive supply chain into one potentially limited only by mining and processing efficiency. Such local sourcing creates a scalable model for building large space structures, from satellite servicing stations to space hotels, fueling a new industrial ecosystem beyond Earth. One concrete example illustrating the synergy between asteroid mining and space construction is the vision of orbital habitats, large, pressurized structures where humans could live and work safely for extended periods. These habitats require durable materials for withstanding micrometeoroid impacts, temperature extremes, and radiation exposure. Metallic asteroid resources could provide both the bulk materials and advances in metallurgy necessary for fabricating protective shells and internal components. Expanding on this idea, manufacturing in microgravity presents unique opportunities impossible to replicate on Earth. Without gravity-induced convection or sedimentation, materials can solidify with fewer defects, enabling the production of superior quality crystals, fibers, or alloys. This could lead to improved electronics, stronger composites, or ultralight structures valuable in both space and Earth applications. The logistics of executing such manufacturing depend heavily on advances in robotics and automation. Building and assembling large structures in orbit will likely depend on robotic arms, drones, and autonomous systems capable of manipulating components precisely. Here again, asteroid mining complements construction efforts by providing feedstock integrated into this automated cycle. Closed-loop life support systems, essential for long-duration space missions, might also benefit from asteroid resources. For instance, water from asteroids can be recycled for drinking, agriculture, and hygiene, while oxygen derived from water electrolysis supports breathable atmospheres. Metals mined could be used for fabricating spare parts or recycling worn-out components, reducing dependence on Earth resupply missions. Extending this concept further, researchers are exploring the idea of space furnaces, facilities that use concentrated solar energy to melt asteroid material and shape it into usable parts via processes like casting or 3D printing. Such infrastructure could operate continuously, providing a maintenance and manufacturing hub for spacecraft and orbital platforms. The Moon is another key destination where asteroid mining can bolster construction and exploration efforts. While the lunar surface offers some in situ materials like regolith and ice, certain metals or volatiles may be scarce or difficult to access. Asteroids could supplement lunar resources, bringing unique materials or higher quantities of essential compounds to support lunar base expansion. On Mars, the case is similar, but even more challenging due to distance and harsher conditions. Transporting building materials and fuel from Earth is extraordinarily expensive and inefficient. Asteroid-mined resources could be delivered to Mars' orbit or the planet's surface to create infrastructure critical for habitats, scientific equipment, and eventually self-sustaining colonies. A fascinating operational model under consideration involves developing orbital logistics hubs near Earth or other celestial bodies. These hubs would receive asteroid-mined materials, refine and process them, then distribute them where needed, whether that is fueling missions, assembling vehicles, or constructing habitats. Such hubs would act much like seaports or distribution centers on Earth, enabling efficient flow and storage of space commodities. Despite the promise, manufacturing with asteroid-derived materials will confront significant technical hurdles. Processing raw asteroid regolith or metals in microgravity demands equipment adapted for low-force environments, stable anchoring systems, and precise thermal controls. Quality control must ensure that materials meet structural and safety standards vital for human occupancy and mission success. Moreover, developing standardized interfaces and modular designs can ease assembly and integration challenges. If spacecraft components and habitat modules can be designed for easy construction using randomly sourced asteroid materials, the complexity and cost of building in space can be reduced. Industry-wide cooperation may eventually lead to shared manufacturing protocols akin to those used in terrestrial construction. An emerging area that ties asteroid mining to space manufacturing is the production of radiation shielding. Cosmic rays and solar particle events pose significant hazards to astronauts outside Earth's protective atmosphere and magnetosphere. Metals and regolith processed into effective shield layers could protect habitats, vehicles, and even spacesuits. Using materials from asteroids for shielding makes transporting massive protective layers from Earth unnecessary, a critical factor as shield thickness often determines habitable volume and vehicle mass. Additive manufacturing technologies, 3D printing, are central to realizing these ambitions. Current experiments aboard the International Space Station, ISS, have demonstrated printing plastic and metal parts in microgravity, and ongoing research is expanding material options and printing fidelity. When combined with asteroid-mined feedstock, 3D printing promises a flexible, on-demand manufacturing capability supporting space infrastructure growth. The circularity of materials usage in space, with asteroid mining feeding into manufacturing, assembly, and eventual recycling, helps create sustainable industrial ecosystems. Unlike on Earth, where mining and manufacturing often generate waste and environmental damage, space industries have the potential to design closed loops minimizing losses and maximizing resource efficiency. Looking further ahead, such capabilities could enable constructing large-scale scientific instruments, deep space probes, or even solar power stations in orbit. These would leverage asteroid materials for both functionality and cost-effectiveness, supporting a broad array of missions beyond human habitation. While the technical and logistical aspects of space-based manufacturing and construction are in early stages, programs led by NASA, ESA, and private companies are actively exploring prototypes and mission concepts. Initiatives such as NASA's Artemis Base Camp Plan include strategies to integrate lunar and asteroid resources into comprehensive space infrastructure development. Ultimately, incorporating asteroid mining into space manufacturing shifts the paradigm from Earth-dependent exploration to a more autonomous, sustainable model. This decreases launch mass requirements, lowers mission costs, and enables longer, more ambitious missions. It also opens the door to commercial opportunities beyond pure resource extraction, spanning manufacturing, assembly, servicing, and broader space industrialization. In essence, asteroid mining becomes not just a source of raw materials, but a foundational element in building the infrastructure that will support humanity's presence and economic activity beyond Earth. As these technologies and systems mature, they will form integral components of the emerging space economy, accelerating our ability to live and work in space in ways that were once the realm of imagination. This intertwining of mining with construction and manufacturing also highlights the importance of developing robust standards and interoperability in space systems. Hardware and processes designed on Earth must adapt to the realities of extraterrestrial environments, and seamless integration between mining outputs and manufacturing inputs is essential for efficiency. Real-world testing, small-scale demonstration missions, and rapid iteration will prove critical in refining designs and operational concepts. By progressively validating components and processes, from mining water for fuel production to printing a replacement satellite part using asteroid metals, researchers and engineers can build a portfolio of successes that pave the way for larger-scale projects. In conclusion, asteroid mining's most compelling promise extends well beyond resource extraction. By enabling space-based manufacturing and construction, it plays a pivotal role in creating self-sustaining space infrastructure, supporting exploration goals, and establishing an economy beyond Earth. This synergy of mining and manufacturing defines a next step in humanity's evolution as a spacefaring species, making the dream of permanent, expanding human activity in space more tangible and attainable. While the integration of asteroid mining with space-based manufacturing promises to revolutionize our presence beyond Earth, it naturally leads to another crucial consideration. How might the growth of these activities affect space traffic management and orbital sustainability? As mining missions multiply, involving spacecraft traveling to and from asteroids, transferring materials through orbiting stations, and deploying manufacturing facilities, the density of human-made objects in space will increase, raising important questions about navigation, collision avoidance, and long-term environmental stability in satellite-filled regions around Earth and beyond. Space traffic management refers to the processes and systems used to monitor, predict, and coordinate the movement of all active and inactive objects in Earth's orbit to avoid collisions and ensure safe operations for satellites, spacecraft, and stations. Currently, with tens of thousands of tracked objects including operational satellites, defunct spacecraft, spent rocket stages, and fragments of debris, managing this traffic is already a complex challenge. Introducing asteroid mining operations expands this environment with additional vehicles, freighters carrying extracted materials, processing infrastructure, and potentially temporary storage modules. One immediate concern is that mining spacecraft, often operating on highly elliptical orbits or in deep space maneuvering towards near-Earth asteroids, must transit through congested regions such as low Earth orbit, LEO, and geostationary orbit, GEO. During these transitions, Accurate tracking and communication are essential to prevent accidental collisions, which could generate debris clouds endangering other satellites and increasing the risk of cascade effects, commonly referred to as the Kessler syndrome, where collisions spawn more fragments that trigger further collisions. To mitigate such risks, mining operators will need to coordinate closely with existing space situational awareness (SSA) networks operated by governmental and international organizations, which track objects and predict conjunctions, close approaches. Furthermore, spacecraft planned for asteroid mining may incorporate enhanced maneuverability and autonomous collision avoidance systems, allowing them to adjust trajectories quickly if warned of an impending risk. Beyond Earth orbit, the establishment of fuel depots or processing hubs at Lagrange points, lunar orbit, or Mars orbit adds new traffic hubs where multiple missions converge. These nodes, while essential for an efficient space economy, represent crowded spaceports where careful scheduling, docking protocols, and communication networks become critical. Without effective traffic management, the risk of operational delays or accidents grows, potentially disrupting mining and exploration activities. The mining itself may also influence orbital environments indirectly. For example, launching return materials from orbit back to Earth or transferring mined products between spacecraft requires predictable, stable trajectories and maneuver sequences. Errors or malfunctions in these operations could lead to unplanned debris or even abandoned objects drifting uncontrolled, complicating the task of keeping orbits clear. To address these complexities, proposals for new regulatory frameworks and operational standards are under discussion. International agreements, possibly building on or expanding existing treaties, could mandate reporting of mining mission trajectories, debris mitigation plans, and coordination with space traffic authorities. Incorporating asteroid miners into a global traffic management system would enhance transparency and safety for all space users. From a technological perspective, improved sensors, radar systems, and onboard autonomous navigation will be increasingly important. Advances in artificial intelligence can support predictive modeling of orbital populations, alerting operators to risks well in advance. Furthermore, developing methods for active debris removal, such as robotic space tugs tasked with capturing and deorbiting defunct objects, could complement mining operations by reducing the overall threat of collision-generated fragments. The growing network of communication satellites, planned megaconstellations with thousands of low-orbiting satellites, and expanding space tourism further intensify the need to integrate asteroid mining missions into comprehensive traffic management strategies. This integration underscores that space is a shared environment where the actions of one player can affect the operational safety and effectiveness of many others. Looking beyond Earth's immediate vicinity, traffic management will also extend to cislunar space and the orbits of Mars and other destinations. While these regions currently see far fewer human-made objects, ongoing exploration and resource extraction activities will increase congestion, necessitating early development of coordination protocols and systems suitable for the unique gravitational, environmental, and operational challenges found there. In summary, ensuring the safe and sustainable expansion of asteroid mining depends not only on technical prowess in extraction and processing, but also on the establishment of robust space traffic management. Without coordinated efforts, the benefits of mining could be undermined by accidents, debris proliferation, and loss of operational integrity across the wider space community. Beyond traffic management, another critical dimension with growing significance relates to planetary protection and the possible contamination of celestial bodies. The field of planetary protection concerns protocols aimed at preventing the forward contamination of other worlds with Earth-origin microbes and the backward contamination of Earth with potential extraterrestrial life or hazardous materials. While most discussions have focused on Mars or icy moons as potential sites for life, asteroid mining introduces unique considerations because many asteroids contain primitive organic materials and volatiles. Mining operations physically interact with these extraterrestrial environments, potentially disturbing surfaces that have remained pristine for billions of years. Although asteroids are generally inhospitable to life as we know it, their organic constituents are scientifically valuable for understanding the origins of life and the chemical evolution of the solar system. Disrupting or contaminating these environments could irreversibly alter or destroy that information. International space policy already includes planetary protection guidelines, set by groups like the Committee on Space Research, COSPAR, primarily to safeguard Mars and other bodies of astrobiological interest. However, as mining on asteroids develops, extending and adapting these protocols will become necessary. Operators may need to employ sterilization procedures for landing gear, limit disturbance to selected zones, or conduct environmental assessments before mining activities commence. Additionally, there is the question of whether mining spacecraft could inadvertently transport terrestrial microbes to asteroids, potentially confounding scientific investigations or affecting the native chemical environment. Conversely, returned samples or materials might pose contamination risks to Earth, mandating stringent sample return protocols and secure containment measures. Addressing these planetary protection challenges is essential not only for scientific integrity, but also to build public trust and international consensus that asteroid mining respects the broader space environment. Future missions will likely include planetary protection plans, continuous monitoring, and transparency in environmental impact reporting. Complementing environmental stewardship and traffic management is the advancement of workforce development and education, which together form a foundational pillar of sustainable asteroid mining initiatives. Building, launching, operating, and maintaining mining missions requires a highly skilled workforce that spans disciplines like aerospace engineering, robotics, geology, materials science, and space law. As asteroid mining evolves from concept to practice, educational institutions and training programs will play critical roles in preparing engineers, technicians, scientists, and regulators capable of meeting the sector's complex demands. Specialized curricula focusing on space resource utilization, autonomous robotics, space systems engineering, and microgravity manufacturing are emerging at universities and technical institutes around the world. Moreover, fostering interdisciplinary collaboration is essential. Mining asteroids is not solely an engineering challenge. It requires integrating legal frameworks, economic modeling, environmental ethics, and international relations. Encouraging cross-field education ensures that future professionals can approach problems holistically, anticipating challenges and crafting balanced solutions. Internships, partnerships between academia and industry, and governmental support for research initiatives will enhance this talent pipeline. Initiatives like NASA's Artemis Student Challenges and ESA's educational programs offer examples of efforts to inspire and prepare the next generation of space resource specialists. Additionally, public outreach in STEM, science, technology, engineering, and mathematics, education initiatives aimed at young students can nurture early interest and broaden participation in space careers. Diverse, inclusive work environments have been shown to drive innovation and resilience, making the diversification of the asteroid mining workforce a strategic priority. Alongside workforce considerations, the development of supply chains and manufacturing ecosystems adapted for space mining is crucial. Traditional mining relies on extensive logistics networks, but in the context of asteroid mining, these chains extend into orbital and deep space environments. Building reliable chains for producing, launching, and replacing mining hardware, transporting extracted materials, and supporting manufacturing in orbit demands new models of supply chain management. Innovations like modular spacecraft, reusable rockets, and additive manufacturing reduce dependency on Earth-based factories, enabling more agile and responsive operations. However, establishing these complex interplanetary supply cylinders requires cooperation among private companies, governments, and international partners. Integrating production capacity, transportation assets, and mission control infrastructure. The experience gained in terrestrial supply chain management, combined with lessons from satellite constellations and the ISS logistics, offers valuable insights into managing inventory, production timelines, and quality control under unique space constraints. In the economic realm, these developments intersect with evolving financing models critical to scaling asteroid mining. Beyond initial venture capital or government grants, sustainable funding may include public-private partnerships, bond issuance, or international investment consortia. Reliable revenue projections tied to service contracts, fuel sales, or material deliveries will underpin investor confidence. In addressing these practicalities, pilot projects and demonstration missions remain vital. Early mission successes can validate technologies, build reputations, and reduce uncertainties, paving the way for broader acceptance and investment. Agencies and companies alike continue to plan missions that progressively increase mining capabilities, refine autonomous operations, and develop in-space manufacturing processes. In conclusion, asteroid mining is a multidimensional endeavor, encompassing not only resource extraction but also space traffic management, environmental responsibility, planetary protection, workforce development, supply chain logistics, and economic innovation. Its realization demands integrated strategies and cooperative frameworks that consider the technical, environmental, social, and economic factors holistically. By advancing in these interconnected areas, humanity moves closer to opening a new chapter in space exploration and utilization, one where asteroids serve not just as distant celestial bodies, but as accessible resources fueling sustainable presence and activity beyond Earth. The successful outcome holds transformative potential for science, industry, and the future of human civilization. Another crucial avenue to explore in the maturation of asteroid mining is the development of economic models and market mechanisms tailored specifically to space-based resources. Traditional commodity markets operate on Earth with established pricing, supply chains, and demand cycles. But when it comes to materials mined from asteroids, these frameworks require adaptation or even reinvention to reflect the unique characteristics of space resources. One foundational challenge is establishing a reliable valuation for space-mined commodities. For metals like platinum or rare earth elements, prices fluctuate based on terrestrial supply and demand, geopolitical factors, and economic trends. However, introducing significant quantities of these metals from asteroids could potentially destabilize existing markets. If a mining operation suddenly delivers large batches of platinum to Earth, prices could plummet, impacting profitability and terrestrial miners alike. As a result, initial asteroid mining ventures may seek to avoid flooding the market by carefully calibrating extraction rates or focusing on more niche applications, such as supplying materials directly for space infrastructure. Alternatively, markets for space resources may develop independently of Earthbound commodities, driven by in-space demand. For example, water extracted from asteroids, primarily destined for conversion into rocket fuel or life support consumables, represents a fundamentally different kind of resource, one whose market is constrained by space activities rather than Earth's industrial usage. Pricing models in such cases would emerge based on operational savings for spacecraft operators, who otherwise would need to lift water from Earth at tremendous cost. This leads to the notion of creating dedicated space commodity exchanges, or trading platforms, where quantities, qualities, and delivery schedules of materials like propellant, metal feedstock, or building blocks can be bought and sold. Such exchanges would require transparent standards of measurement and certification, ensuring that buyers know the exact characteristics and provenance of the resources. In essence, this would mirror how terrestrial commodity markets operate, but with added complexity due to orbital dynamics, delivery windows, and risk factors associated with space operations. Insurance and risk management are tightly interwoven with economic models. Space mining ventures face uncertainties including launch failures, hardware malfunctions, variable asteroid composition, and regulatory shifts. Insurance products tailored to these risks, covering asset loss, mission delays, and liability, will influence financing conditions and project viability. Investors will naturally demand risk premiums or guarantees that shape the pricing and contractual structures within space mining markets. One interesting economic model under consideration is the concept of resource leasing, rather than outright ownership and sale. For example, mined materials stored at orbital depots could be rented to exploration missions or satellite companies needing temporary supplies, allowing flexible use without upfront purchase of large quantities. This leasing approach could enhance liquidity in the market and reduce the capital tied up in ownership, smoothing cash flows and encouraging experimentation. Public-private partnerships also appear poised to play a significant role. Governments interested in promoting sustainable space exploration might contract private entities to supply propellant or construction materials derived from asteroids, providing a guaranteed revenue stream that underpins early mining operations. Such arrangements reduce investment risks and align commercial incentives with strategic exploration goals, accelerating technology development and market creation. Moreover, as asteroid mining scales up and matures, new economic sectors may arise that go beyond raw materials. Space-based manufacturing and assembly, servicing and repair of satellites using in-space resources, space tourism supported by refueling and infrastructure, and even scientific endeavors requiring rare isotopes could all form part of a diversified space economy. Each of these markets would interact with asteroid mining outputs in complex ways, driving specialized demand and influencing overall sector profitability. An important consideration within these models is the timing of returns. Mining missions typically demand upfront investments in spacecraft, technology development, and launch costs, while revenues may take years to materialize due to mission durations, processing times, and market establishment. To attract capital, companies must provide clear pathways to profitability, often through staged or milestone-based funding, with gradual scaling of operations. Case studies from other industries, such as deep-sea mining or oil exploration, offer parallels regarding how uncertain initial investments can ultimately lead to viable industries given technological advances, regulatory clarity, and market development. However, the even greater distances, communication delays, and environmental challenges of space make these comparisons only partial guides. On an international scale, economic models must also grapple with questions of equity and access. If asteroid mining becomes highly profitable, how will wealth derived from space resources be shared or regulated? Discussions under global bodies like the United Nations seek to ensure that space remains a province of all mankind, balancing commercial interests with broader public benefits. The emergence of economic frameworks that foster fair competition, encourage innovation, and share benefits internationally is critical to avoiding monopolies or conflicts. Looking further forward, the integration of asteroid mining economics into planetary-scale resource management is an area worth considering. As humanity's demand for resources grows and terrestrial reserves fluctuate, having off-world supplies could act as a buffer against supply shocks, price volatility, and geopolitical tensions. Diversifying resource sources across Earth and space might contribute to global economic stability, environmental conservation on Earth, and support for sustainable development. Transitioning from economic modeling to the practical domain, the question of mission architecture becomes paramount. Designing mining missions that optimize cost, efficiency, and return requires multi-layered decision-making, encompassing spacecraft design, propulsion methods, mining techniques, and target selection. Each element influences the overall economics and feasibility of asteroid mining. For instance, spacecraft propulsion choices significantly affect mission durations and energy requirements. Traditional chemical propulsion provides high thrust but at the cost of heavy propellant loads, which limits payload mass. Conversely, electric propulsion systems like ion thrusters offer higher efficiency and lower propellant mass fractions, but produce lower thrust, leading to longer transit times. Balancing these trade-offs requires analysis of mission priorities, whether speed, mass, or energy consumption dominates. Similarly, the choice of target asteroid impacts mission complexity. Near-Earth asteroids with low delta-V requirements are favored for early missions because they reduce travel time and fuel usage. However, not all NEAs contain the desired materials or in quantities sufficient for profitable mining. Asteroids with richer resources might lie farther afield, posing greater logistical and technical challenges, but offering higher long-term returns. Furthermore, mission designs may adopt multi-phase architectures, with initial prospecting missions to gather detailed data, followed by construction and deployment of mining apparatus, and then regular extraction and processing operations. Such phased approaches reduce risk by validating each step and allow incorporation of lessons learned before scaling up. In transport logistics, a combination of small, reusable spacecraft ferrying mine materials and larger, centralized processing stations could form an optimized supply chain. For example, mothership orbiters equipped with refining facilities might receive bulky raw material from mining robots, convert it into concentrated products, and transmit the refined goods either to Earth or to other space facilities. As technologies develop, flexibility in mission architecture becomes ever more valuable. The capacity to adapt to unexpected asteroid surface properties, hardware malfunctions, or market changes requires modularity in spacecraft and mining equipment. Designing systems that can be upgraded, repaired, or repurposed extends asset life and improves return on investment. Another emerging area is the exploration of alternative propulsion and capture methods that might enhance mission efficiency. Concepts such as solar sails, which use radiation pressure for propulsion, or gravitational assists using planetary bodies, could lower fuel requirements for cargo transport. Additionally, techniques for gently parking mine materials near Earth orbits, such as using Lagrange points as safe staging areas, help streamline processing and distribution. The integration of remote sensing technologies and AI into mission control further enhances responsiveness and efficiency. Real-time data analysis allows mining spacecraft to adjust operations dynamically based on changing conditions or discoveries, maximizing yield and minimizing risks. These considerations illustrate that successful asteroid mining depends not just on individual technological advances, but on comprehensive mission systems engineering that coordinates multiple components into efficient, flexible, and economically viable operations. Beyond mission planning, fostering global collaboration emerges as a strategic imperative for advancing asteroid mining. Given the high costs, technical complexity, and regulatory uncertainties, cooperative efforts among nations, space agencies, industry players, and research institutions can pool resources, knowledge, and infrastructure to accelerate progress. International partnerships facilitate the sharing of risks and benefits, enable standardization of technologies and operations, and promote peaceful use of space resources. For example, joint missions can combine expertise in astronautics, robotics, and planetary science, while collaborative legal frameworks can harmonize property rights, safety standards, and environmental protections. Programs like the Artemis Accords demonstrate how agreements establish principles for space exploration, including commitments to responsible resource extraction. Though primarily focused on lunar activities, the frameworks laid down can inform and extend to asteroid mining endeavors. Multilateral organizations such as the United Nations and related committees continue discussions on governance of space resource utilization, seeking to create inclusive, transparent mechanisms that support innovation while safeguarding equity and sustainability. Moreover, joint missions reduce duplication, allowing faster technology maturation and reducing costs. Shared data from reconnaissance and prospecting missions improves target selection, operational planning, and risk management. Cross-border supply chain development leads to robust, diversified industrial bases supporting mining hardware production, launch services, and permit processing. On the commercial side, consortiums and alliances bring together companies with complementary strengths, pooling capital and expertise to overcome financial and technical hurdles. Such coalitions may also wield greater influence in shaping regulatory regimes and securing government contracts. Importantly, collaboration fosters knowledge transfer between experienced and emerging spacefaring nations, contributing to a more diverse and resilient space economy. This inclusiveness broadens participation and helps mitigate geopolitical tensions that can arise from competition over scarce resources. As asteroid mining moves from concept to execution, embedding the principles of international collaboration, transparency, and shared stewardship in all phases, from research and development to operation and resource distribution, lays the foundation for sustainable industry growth aligned with humanity's broader spacefaring aspirations. In conclusion, asteroid mining represents a multifaceted challenge and opportunity. Economic models must evolve to accommodate space-specific factors and develop vibrant markets that sustain operations while balancing terrestrial impacts. Mission architectures integrating novel propulsion, autonomous systems, and modular design optimize technical and financial performance. Collaboration across borders and sectors catalyzes progress, fosters equity, and ensures responsible stewardship. By weaving together advances in economics, engineering, governance, and cooperation, humanity inches closer to unlocking the vast material wealth stored in asteroids. This achievement promises to reshape our relationship with space, transform scientific exploration, invigorate global economies, and provide the raw materials that underpin humanity's expansion beyond Earth, setting the stage for a new era in space utilization and discovery.